So next up is John Readey with the HDF group, who's going to share with us about the RESTful and connecting to the cloud and sharded storage for HDF5.
Right. Hello. Let me share my screen. One second. Okay, you guys see that?
Gotcha.
All right. So I'm going to talk about the RESTful for HSDS and HDF sharded data storage, which seem like two entirely different topics, but you'll see they come together. Yeah. So first I'll talk about the sharded data storage, then RESTful, and then this new project called Direct Access. So the idea of sharded storage is that rather than the traditional view of storing all the HDF5 objects within a single POSIX file, you store each object as a separate file. If you're using a object storage like S3, there'll be a separate object, but the same idea. If the object is metadata, for example, data sets along with its type and shape and so on, is stored as JSON. If it is chunk data, they're stored as binary objects, because obviously for large chunks, it'd be very inefficient to store those in a textual form. So you might say, well, won't this be like an explosion of files, right? You'll have millions of files potentially, and yes, you do, and we do, and it worked pretty well. For example, in the NREL presentation, they created air quote files in this format that are have tens of millions of objects. So what's the motivation for it? Well, one nice thing is you can limit the maximum size of any object. So even with POSIX, it can be problematic if you have a POSIX file that's 50 terabytes in size, right? It's very problematic to deal with that in any reasonable file system. If you are storing this in an object storage system, typically they require any object to be totally rewritten anytime there's an update. So if you have large files, let's say you have a 4 terabyte file, and you have to write 4 terabytes every time you modify an element, that will be extremely slow. Another motivation is that it makes parallelism a lot easier, right? You don't need to lock files if you've organized your workers such that each worker has a partition of files to work at. Also, a lot of the complexity, it seems like in the library, is dealing with managing the free space within an HDF5 file and key value mappings and so on, right? If you are letting the storage system do that for you, that removes a ton of complexity with implementing the HDF5 semantics. Another benefit is that with the library, there's this problem of similar to disk drives when there's holes in the storage space, right? If you have, say, a data set, an HDF5 file, and you delete that, now you have the same size HDF5 file, but it'll have this free space in the middle of the file. And there are tools to compactify the file, but in general, it's a little problematic. Another advantage is that you don't have this issue of, say, your server crashes and the file is left in this bad state, where it's no longer possible to read the file with the library. At least with object storage systems, each write to a file either succeeds or no change is made. And so you don't have this problem of ending up in a corrupted state with your storage. Case against sharded storage, well, I guess there's a convenience, right? And I guess this is one of the benefits of HDF5 when it first got started. You have one thing to pass around that contains all your data. But maybe if you think of this, if you have the right tools that abstract this concept of files, that's not maybe such a big issue, right? So if you're using, say, HSDS to manage this set of objects in an S3 bucket, you're generally not looking at that bucket. You're not dealing with the content at that level. You have an abstract handle to that content, and you can do all the typical HDF style things that you need to do with that. File systems maybe previously were challenged if you had thousands or millions of files within a directory. I'm not sure that's a big problem with modern Linux file systems, and certainly not a problem with most object storage systems. So here's an example of what this looks like. So again, this is kind of like the key value mapping, like Jerome was talking about with Deos. You have a key, and in a key, you can have files or objects, and they can have sub-objects and so on. So we have something like group.json that would store metadata for a group. We have a dataset.json that can metadata for the JSON. And then for the chunks, they're just stored at these keys, which is basically the chunk index within that data set. So we don't need to, just like with HDF5 library, if you create a large data set, these chunk keys are written on demand, right? So you only start filling up this space of chunk keys as you're writing data to the data set. One thing that strikes some people strange is that this hierarchy isn't like the hierarchy you have with HDF5 groups and subgroups and data sets. And that's so we can efficiently support multi-linking. So if you have, say, two groups that point to the same data set, that works very well here. If you had something where you're actually trying to map the HDF5 hierarchy into the storage schema, it'd be a little problematic. Another advantage is that if you are deleting links or renaming links, you don't need to move anything around in the storage system. As I was talking about, if you have a bunch of workers, it'd be kind of nice if you could divvy up all the objects in your storage hierarchy so that each worker has a roughly equivalent number of objects to deal with. And there's this called Prush algorithm approach. So we take that key, hash it, take the modulo by the number of workers, and then each, for any particular key, you have a worker to assign that object to. So the nice thing here is decentralized. You don't need some kind of central bookkeeper to keep track of who owns what. It just works based upon these key values. So if we have HDF5 files, maybe we want to convert to this sharded format. We have a tool, hsload, that takes a HDF5 file and does this conversion using the HSDS server. And if you want to go back to HDF5, you can use hsget, which will do the reverse. And the data is preserved after this round trip. Sorry. It's maybe not totally exact. I think the chunk layout may change a few minor details, but basically you get back what you started with. If you have like a bunch of large HDF5 files, doing this conversion is rather time consuming. And then you're going to wind up with double the amount of storage, assuming you don't want to get rid of the original HDF5 files. So we support this idea of linking to the source HDF5 files. The hsload works like before, and it gathers up all the metadata. But rather than copying the chunk data, we just store links back to the location of that chunk in the original HDF5 file. Then when reading dataset data, we do a range get, which is basically reading that portion of the file out of the file. And then from then on, the same kind of processing goes as with regular ingested data. Okay, so that's the sharded data format. Next, let me briefly talk about the RESTful plugin. So as we've been talking, it's a vol implementation. The advantage here is that for HDF applications, they can use the same API, and as we've seen, minimal code or no code changes, and they can start reading and writing data into the sharded format. The RESTful is here on GitHub. There were some changes to the vol API in 1.12. So for linking with the HDF5 1.12 version, there is a branch, HDF5 1.12 update branch on GitHub. So the feature support is rather good, I think, for the RESTful, but there are a few things that are not yet supported. And I wanted to lay out things that are supported in HSDS, but not the RESTful, and also things that are supported in, say, H5PD, but maybe not the RESTful. So object references are supported on HSDS, they're supported in H5PD, but not in the RESTful. Region references are not yet supported in HSDS or H5PD or RESTful. So region references, for example, would need some additional work on the server side in addition to work on the client side to support. Fill values are supported in HSDS and H5PD, but not in the RESTful. Virtual datasets are quite complex to do, and we haven't done that work yet on the server side. Variable length data types are supported on HSDS, H5PD, but again, not in the RESTful. And then two things I put asterisk because I don't think they have defined vol entry points yet. In HSDS, we support SQL-style queries to select rows out of a data set that meet certain restrictions. That's supported in HSDS and H5PD, but not in the RESTful. And lastly, dataset append. So if you have multiple writers, it's convenient to be able to have an append operation that can work without, say, writers potentially overriding each other's appends. So that's a feature we have on server and H5PD, but not in RESTful. So a fair bit of work that'd be nice to do. And given that the HDF group has limited resources to do everything we would like to do, I would welcome anyone out there who would like to contribute to this project. So just submit a pull request or contact me, and I would love to knock some of these off the list. In addition to kind of HDF feature support, things that I would really like to have with the RESTful. Supporting multi-threaded clients. So I think this locking issue in the library, it's there, I feel, mainly support the native driver. Vols that do not need that kind of high-level locking would be great to get rid of it, but I don't think that's currently yet supported with the library. We just talked about the asynchronous API. It sounds like we would need specific support in the RESTful to work with async calls. Quincy mentioned eval can be activated based upon environment variables, and that's nice, but I would also like to see a scheme where the vol is activated based upon a certain file prefix, right? So if you open a file, for example, it says HDF5:// that should be like a clue to use the rest vol as opposed to the native driver. Paginated read-write for large data operations. So with the library, it's very possible, say, to write 10 gigabytes in one call. And the library will just take however long it takes to do that, and you're done. When things have to go across as HTTP requests, and you have possible timeouts or limits to how much memory can be ingested in one call, that's problematic. So what we do in H5PD is that we paginate large read requests. Something similar would be nice for the rest vol. And as you know, on the internet, things break occasionally. So you might get a timeout or the server is unavailable, and it would be nice to have retry logic. So for intermediate errors, we just retry the call and hopefully succeed the next time. There are special connectors for Java and .NET and R that work with the HDF5C library. And I would like to make sure these all work well using the rest vol. And finally, it'd be nice, just like with Deos, if tools like h5dump would just work with the rest vol. Okay, and finally, I want to talk about this direct access project. So now we can access this sharded data store using HSDS, right? And servers are wonderful in that you have the server that mediates access to a storage system, right? So for example, in KetoLab, you don't have authority to directly write to the S3 bucket, but you have an account with KetoLab, and that server has the ability to write things that you're allowed to write to on that storage system. With a server, you can have a large cache to speed up recently accessed data. You minimize data I/O between the client and the server, right? So if I'm on my desktop and I'm doing, say, a time series extraction over a really large file, the bulk of the data I/O will happen between the storage system and the server, and a minimal amount of data comes from the server to my desktop. And that's very handy if your bandwidth is limited or if you're paying egress charges and so on. And if you're running the server on HSDS on a large server or a cluster, you have more processing capacity and memory than your client is likely to have. And you can take advantage of that to improve performance. And especially for multi-writer, multi-reader programs, HSDS serves as a synchronization point so that you don't have the writers overwriting each other's content. This is all great, unless it's not great, right? And when's it not great? Well, maybe I don't want to bother setting up and running the service, right? The other challenge is capacity scaling. If I have a server and it's running fine with 10 clients, and suddenly 1,000 clients show up, I may have a problem in that that server doesn't have the capacity to handle that amount of load. So we have this idea of a direct access functionality. This would provide equivalent functionality to HSDS, but it would all run within the client side. And this idea, we would take the SN code, run as a subprocess, take the DN code in the server, run it as one or more subprocesses. Right? For example, if I have a 4-core system, I could run 4 DN nodes to maximize my throughput. The subprocess would have the ability to directly access the storage system, either the S3 bucket or even like a local POSIX drive. Communication between the parent process and subprocesses would be by HTTP, just by local hosts, right? They wouldn't go outside the server. When the last file is closed, these processes would shut down, and the same storage schema as HSDS would be used. So this enables you to easily switch between the direct access mode and a server-based access. So this is
Hey, John, we're running a bit late here, so if you can.
Okay, yeah, one more slide and I'll.
Cool.
And this is how it would work with direct access. So these green boxes are subprocesses, and they would write to the storage system. And it would be nice also, so this is, I think, first implementation would use H5 but we could very easily do this with a vol plugin, either a new vol or somehow modifying the REST vol to enable this. Okay, thank you.
That's great. Thanks, John. Maybe we can defer questions to the chat window. We're a few minutes behind. I don't know if there was a quick one we could handle in there. Anybody want to jump in? Okay. Thanks again, John. Looks cool.